This will be the last section that we talk about in sound. This is going to be on interference and then also the Doppler effect, and we'll look at those separately. So the first thing we'll talk about is interference. We've actually already talked about this a little bit, so I'm not going to spend a lot of time on it. Interference in general, we've talked about, is just when two waves overlap, so superposition of waves. In that, you can have constructive interference, where you have larger waves when they overlap, or you can have destructive interference where those waves cancel each other out. So on this first one here, we have, it's actually kind of backwards. This is A and B on the bottom. When you add them together, you get the top one. So this would be constructive interference when the waves are lined up. Another term they say for that is to say that these waves are in phase, so that when they add up, you get a larger wave for their addition. On the second one, this is destructive interference. Again, if we start with the bottom, we have two waves that are opposite of each other, or you could call them out of phase, and when you add them together, they will exactly cancel each other. So that would be destructive interference. The reason I bring that up here at all is so that we can talk about a special case of interference called beats. Here's the definition. So beats happen when you have two frequencies that are very close to each other, that you get kind of a rhythmic, loud and soft tone. That's something that you really need to hear to understand. So I pulled up, so here's a little video from MIT showing the beat frequency phenomenon. I tried to record this before and the sound from the computer didn't record, so hopefully it will this time, and I'll just splice it in the original video. So here he's got two tuning forks. Originally they're the same frequency, so he's going to hit one and then he'll hit the other one. On this one there's this little metal clip, and that changes the frequency just slightly. So that's going to give you two very close but different frequencies, and that's when you're going to hear the beat frequency phenomenon. So here's what it sounds like. So you only hear the beats when there's the two tuning forks together. If he had only played the one on the left by itself, it would sound just like the original tuning fork. It'd sound like a normal tuning fork. It's only when they're played together that you hear the beats. Here's a picture of what the waves look like when they overlap. You get these kind of football looking things. That's the interference pattern. And if you haven't done it yet, you will at some point do in the lab. We're going to actually look at those beats, and you'll create them for yourself and have a chance to see what they look like. Here's the equation for beat frequency. This is a nice equation because it's very simple. So the beat frequency is equal to the absolute value of the difference between the two frequencies. So there's no negative beat frequency. If the difference between the two frequencies, let's say that one frequency was 200 and another one is 205, the beat frequency would be 5. There's no negative 5 or anything like that. It's just 5. So it's a pretty simple deal. Here's an example problem where you would see these. So here we have two notes emitted by two tuning forks. When one of the forks vibrates at 380 hertz, the listener hears a beat frequency of about 5 hertz. What are the possible frequencies for the second fork? Now, I very nicely wrote down all of our knowns and unknowns in our equation, but this is one that you should be able to think about. So if one's 380 and the beat frequency is 5, the other tuning fork has to be plus or minus 380 plus or minus 5. But here's how the numbers would work out. So there's my original frequency and the beat frequency, there's my nice equation, and then I know either one of those could be the other tuning fork. There will be times where they'll give you a problem and they'll give you a hint as to which of those two they want you to use for the answer. So they might say something like the beats increase when one of the tuning fork frequencies increases. So you would figure out, oh, so the original tuning fork must have been less than the one that than the second one. They'll give you some little hint like that to help you figure out which one they want, or they might ask for both. It just depends on the question. The second and the bigger topic for this video is the Doppler effect. The Doppler effect is what you hear. You've heard this probably on the news when you hear like on the weather. They use Doppler radar. They usually name it something cool like Doppler radar 3000 or something like that. That is they're referring to the same thing that you hear if you're sitting still and you hear like a police car go by, and the siren sounds different when it passes you. If you were in the cop car and you were, putting your sirens on, you would hear it just normally, like the pitch wouldn't change. But if you're an observer and you watch the cop car go by, you'll hear it go from a higher pitch, and as it passes you, it'll be a lower pitch. Another example of that is a race car. You hear a race car drive by you, it'll hear like zoom, something like that, where the pitch will change because of how you hear it. So that is the Doppler effect. So definition is the perceived difference in frequency due to the movement of either the source or the observer, and I'll explain that as we go. First thing I wanted to show you is a little applet on that. An applet is just a little program, a really simple program. So if I click here, I get a little airplane, and it's putting off a frequency. So if I were on the right side of the airplane, I would see a wave go by, wave, 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 wave. If I were on the back side, I would see that same thing, wave, 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 wave. So the frequency of the waves for the observer is the same regardless of where you're at. Now if I put the plane in motion, that changes. So I'll move it here. And again, if I observe the wave right there, I see wave, 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 wave. So that's a higher frequency. If I do it behind, I see wave, 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 wave. So the frequency becomes much slower from the back because of the motion of the airplane. So I can increase that. And at the top right hand corner, you can see they're comparing the velocity of the airplane to the speed of sound. So I can go right at the speed of sound. That's also called Mach 1. And you'll see on that's when the plane flies at the right speed to basically catch up with the waves. So if you're standing down at the bottom here, all of a sudden you would hear boom. That's your sonic boom that you would hear if an airplane were traveling that fast. Past you, there'd be a big pressure wave that kind of goes by you. It can also make it go faster than the speed of sound. Let's see if I can, let's go about Mach 2. That would be twice the speed of sound. And you'll see it still makes a line down here. This is a pressure wave, and you would hear that sonic boom there, but you can see it's kind of outrunning its own sound waves that would be going faster than the speed of sound. So going back to the Doppler effect, so the Doppler effect then is how you hear sound due to motion. So, and we're talking about sound, but that's actually true for light and any other wave as well. So here's the basic equation. When you see this, don't freak out and say, F prime, is this a derivative? No, it's just another symbol that they use for frequency. So here you have this regular F, this is the actual frequency that would be being produced. This is the perceived frequency, so that's what they mean by the F prime. So that's what you hear, even though that's not the frequency that's actually being given off. So you have those two frequencies. Both of these V's are the speed of sound. Typically you use 340, you can use 345. Honestly, the difference between those is so small, it's not going to make a difference in your answer. Sometimes a problem will tell you exactly what to use for the speed of sound, but in general, pick one, 340, 345, it's not going to matter. Then here you have VO and VS. So VO is the movement of the observer, S is the movement of the source. So you have to take those into account as well. Oftentimes one of those will be 0, which makes the problem a little simpler. When they're both something else, it makes it a little more complicated. So this is the equation written out. Below you have a sign convention, and I will give you this on the test. You don't have to memorize this, but this is important. You have a sign convention means you have to do the signs this way in order to make the problem work out. It's a convention. There's not really a physical reason for it, other than that just kind of makes the equation work. So for this equation, the sign convention is that you have to make the speed of the observer and the source positive when they're moving towards each other and negative when they're moving away from each other. And I'll show you how that works out on an example problem. So here's a quick example. So we have a train traveling at 60 miles per hour. Don't you hate it when they put miles per hour in a physics equation? So you know right off that you're going to have to convert that. Anyway, the train is traveling and emitting a sound at 600 hertz. What frequency do you hear as it approaches, and what frequency do you hear as it moves away from you? Sometimes in these questions they'll only ask you for one or the other. So this one they're asking you for both, towards and away. So here's our givens. I went ahead and converted the speed of sound from 60 miles per hour into 27 meters per second. You can do that on your calculator with your SciTools app, or you could do it if it were not a test situation, you can use Google or whatever to convert that as well. They don't say that the observer is moving, so you can assume that the velocity of the observer is 0. So here's just our plain equation, and I put the numbers in that equation on the next slide, so I'm going to keep clicking through to that. So for part A, so we're looking for what we hear. That's the perceived frequency. The actual frequency was given. I'm using 345 for the speed of sound here. The observer is not moving, so that's 0, and the source is moving. Now notice it's moving towards us in this problem. So that's a positive 27, but the minus sign was already in the equation, so I have to leave that minus sign in there. So I do the math on that, and I get 651. Now you can always check to see if you have your signs correct, in that if it's moving towards you, the perceived frequency should be higher than the original. So if I had solved this equation and had something less than 600, that would make me suspicious that I made a sign error, and you'd want to check that out. So that's something you can kind of use to check yourself. Part B, same thing, except now moving away, I have to flip that sign. So now the minus sign was still in this equation, but now it's minus a negative 27. So I've made a little note there. So that's minus a negative 27, which is how that comes out to be a positive 27. Here I get 556 for the frequency, which is lower than the original, which is what I would expect. So those are the kind of problems we'll have with the Doppler effect. They can be a little tricky in their wording. See, these probably you'll have to pay more attention to than most of the other problems in the chapter. But once you get used to that sign convention, I don't think they're too horrible. So there'll be a worksheet associated with this. Then we'll practice the whole chapter together, and we'll be ready for the chapter